Hello? Okay, now it works again. Okay, let's just start over again. Yeah, so my name is Emil. I'm here to talk about password hashing. Now it works. Okay, so when I'm not talking about password hashing, I'm the technical founder of a company called Commodity Trader, and what we do is that we sell grain online. So you can come to us and you can buy a whole ship of grain, and we will ship you 500 tons of, I don't know, soybeans, and you can put them in your backyard, or you can eat them, or you can feed them to your cows or pigs or whatever. So yeah, that doesn't sound very interesting when put like that, but what I'm going to talk about today is password hashing. And password hashing is like a special field within cryptography. And to make Commodity Trader extremely safe, we use a lot of cryptography in there. So if that's something you fancy, then come and chat with me afterwards. Online, I'm known as Emil Bayes, and that's why on the program it also says my name is Emil Bayes, which is, there's a mathematician called Thomas Bayes, and I've studied math and all that, so I was trying to affiliate with him, but it's not my real name. Yeah, and I'm from Denmark. So yeah, I used to study math, and I love math, but it's because it makes people cry, because math is really hard sometimes. Today, fortunately, we're not going to talk very much about math. It's more going to be about logic and some hard-learned lessons in the real world. So passwords. The thing with passwords is that today everyone has passwords, right? And passwords, we use them to prove your identity, because when you log into a website, it's not like when you go to the airport or wherever, you don't have your passports with you, right? So you use a proxy, you use something, a secret that only you know, and because only you know it, it's logical that you are the person you say you are, right? And they're so ubiquitous now that everyone has passwords. I mean, even my grandmother has a password, right? And that's also the problem, is that all these people, they have to choose passwords, and they have not just to choose one password, but they have to choose a lot of different passwords. And people don't really do that. They just choose one password and use it everywhere. And that's the problem, because if one of the sites you use your password on is compromised, and your password is stolen, and you use the same password everywhere, then suddenly whoever stole your password can impersonate you everywhere. So maybe you use the same password for Facebook and your online banking. That's a pretty big issue if your Facebook gets hacked. So what can we do about this? Well, I see there's like 3 things we can do. We can try and eliminate all security holes in all of the software we use. And these security holes are not just confined to software, they're also confined to processes and people. So the people working at these companies, you also have to be 100% sure that they can't steal your password somehow, or reset the password, or like impersonate you. The other thing we can try and do, and that's something that a lot of tech-savvy people started to do, is to use unique passwords. So you use a password manager, right? You have one master password that you never share with any company, or only with your password safe. And in there you keep a lot of cryptographically random passwords. So if one gets stolen, it doesn't compromise your whole online personality. And the last thing is that we can store the passwords in a safer way. And that's what I'm here to talk about. So, because I mean, the first one, pretty unrealistic, right? At least in the short term. Unique passwords doesn't really work for everyone, only for tech-savvy people. So safer storage is like the last option we have. Here's a quick question, or like a puzzle. What do all these companies have in common? Yeah, they were hacked. So the issue is that I'm not really going to blame them, because if you look across all the big companies now, at some point you have to work, or well, when you build a big company, and we do the same in Commodity Trader, you have to work on the hypothesis that you eventually are going to get hacked or breached. So what's your contingency plan? What's going to happen when you get breached? And if all these companies had used very, very strong password hashing functions, then it probably wouldn't have been as big an issue as it was when all of these got hacked. So we're going to get back to them later. So yeah, this is the Lego hacker guy. This is the guy we are trying to protect ourselves from. So let's talk about the first way that we can build a password system. So the first way is what you in cryptographic lingo would call plain text. Plain text is like really simple. I'm just going to show you what it's about. Here we have a script. I've just put in like a small database, which is just like a map. We're going to work with two functions, right? We have a register function when people sign up to your service, and then we have a login function, right? So when you register, you give your username and your password, and we store your password for you. Next time you come back and you want to authenticate yourself, you give us your username and the password you used. We look up in our database, do we know this username? If we don't, then of course we can't log people in. If we do know the username, we can look at the password we saved, and we can check that it's equal to the password they presented to us this time around. And if it's not, then of course we're not going to authenticate them. And if it is, then we are. So that's all pretty simple, right? Everyone's done this. Let's just see. This is like the general model that we use for this talk. So I'm just going to show that okay, this works because first we register me with my secret password, which is just secret. And then I try to log in, and of course the first time around it works, the second time around it doesn't work, even though the two passwords are very similar. Also notice here I use buffers, and that's something I'm very conscious about. Buffers is like a way in JavaScript that you can almost reach raw memory. It's still garbage collected and all managed for you, but if you want to, you can go in and you can override the bytes. So if you take someone's password in, and when you're done with it, it's not a good thing to have lingering around in memory, because if an intruder is inside the system, they can just sit there and they can watch for people to log in, and they can just snap up their passwords. So you want to get rid of the password as soon as possible. It's like radioactive waste. So, okay, but we all know this is a pretty bad idea, right? We can see the threat model. You have a disgruntled employee, or you have a rogue sysadmin. They just go into the database, read out all the passwords, and you bust, right? So that's pretty silly. So, but apparently not silly enough, because these companies all save passwords in plain text. Some of them even save people's credit card information in plain text, and that was all stolen. So, yeah, you tell me. Problem, plain text, pretty obvious. What can we do about it? We can try to obscure the password. So some people might say that we encrypt the password. That's not what I would call it, or the method I would use. I'd use something called hashing. So a hash, or a hash function, is a special mathematical function that has some pretty certain properties. It's deterministic. That means that the same input is always going to give the same output, right? You want the function to always return, like you don't want to behave randomly. You don't want it to take into account like the time of the day, or like, I don't know, its position in the universe or whatever, right? It's pretty obvious. Next thing is what you in cryptography call preimage resistant. So it means it's one way. If you get the output of the function, it's going to be really fucking hard to predict the input. That's pretty important here, because when we save the output in the database, if people steal all the hashes in the database, you don't want them to be able to figure out what was the input, what was the password that corresponded to this hash that we saved. So one way is pretty important. Then we have something called the second preimage resistance, and that's about voluntary collision. So that's if I know there's a hash in the database, I don't really know what the message was, but can I find another message that gives me the same hash? So can two different passwords authenticate to, or hash to the same value, so I can authenticate even without knowing the correct password? And the last one is collision resistance. You don't want a hash function to give you the same hash for different input. That's pretty important, because you always want it to be one way, right? One way and map to one thing. So I spent a couple of years of my life learning how to write this in math, and this is the last 4 points, just explained in math. It just means that we have a bunch of ones and zeros, right? Bits and bytes. And you can have infinite amount of them with a star, and it maps them over to like a constrained hash value, so it only has a certain number of bits in there. These are a couple of hash functions. You might have heard a couple of them. Maybe some of you have heard of MD5. A lot of people used to implement password hashing functions with MD5. I'm 23 years old. I was born in 1993. MD5 was utterly broken when I was still wearing a diaper. So that was in 1996 that people started to expect, okay, MD5, probably not that good idea. Then you have SHA-1. Maybe you've heard the news recently about the shattered paper. SHA-1 was also not completely broken, but it had there was an attack that was effective on SHA-1, which means that a lot of SSL certificates are going to be pretty screwed pretty soon. Then you have a bunch of other hash functions you might have heard about. They don't really work in our case. We are trying to hash passwords. All these functions are designed to be very, very fast, so you can use them for cryptographic fingerprinting, but it's not that good of an idea to be very fast when you're hashing passwords. So if you want to do well, you can choose one of the last couple of functions, and Argon2 is the one I have something to say about. Oh, wait, hang on a second. I just want to show a demo. So this is a quick way to, here I'm just going to use MD5 because a lot of people know about MD5, even though it's completely broken. Never do this, never put this into production. But it just goes to show how you would go about hashing with the built-in crypto module in Node.js if you were to hash anything but passwords. And if we just run this, then it just gives the same output as before. The good thing about this is that if the rogue sysadmin I was talking about before, if he goes in and steals the database, it won't contain the actual passwords, it will contain the hashes, and that also goes to show down here in the login method. So when you log in, you have to perform exactly the same calculations as when people registered. You have to hash the password again right and compare the hashes. All pretty trivial, you probably all tried this. So yeah, this is like the short form. This is exactly what's needed to do this. These are the offenders. These are the companies that did this in 2016 and thought it was a good idea. So yeah, the problem is that it's very, very easy to break this kind of cryptography. Because we just hashed all the passwords into our database, we can make an attack called well, we can try and brute force all the passwords and see if can we just guess the password. So it's really hard to take the hash and figure out what was the password by going backwards. But what if we just try a bunch of different words and try and go forward? So we can just hash a whole dictionary. And when you hash a whole dictionary, it's called a rainbow table. And you just go into the rainbow table, take the hash you've stolen, look out in the rainbow table, see, okay, what was the hash in your dictionary, and then you got the password. And the thing I wanted to show with before, so this 02, that was the MD5, and you can see that's pretty quick, right? Then I've also made the dictionary attack, and here I'm trying to break my password, and you can see it only took me about 2 seconds on this crappy MacBook. So this was for MD5. A lot of the other cryptographic hash functions that are not password safe are going to be kind of the same. They're all designed to be very, very fast and very, very efficient to run. So, bad idea. Okay. So, what can we do about it? Problem is the rainbow tables. Well, what if we make passwords that are identical, hashed to different values, like some way to obscure, because this would help us in making the pre-computation of the rainbow tables very, very impractical, because you'd have to check it with all these different ways of hashing, and this is called salted hashing. So, oh, wait a second. That's the wrong one. So salted hashing, it runs pretty much as fast as the other one when you're not salted, because you're just adding a bit of extra text. You can see here, this is the code to do it. It's very simple. You get a salt. A salt has to be a cryptographic random value. Nobody has to remember the salt except your database. So you can just generate a bunch of random bytes, not using math.random, but using an actual cryptographic secure random number generator. So that's easy to do in Node. Just call the crypto.random bytes. You put when you hash the password, you put in the salt, and you put in a delimiter, and you put in the password. Then you have a salted password. The salt is not a secret. You could reveal it to anyone. The point is just that every single user has a unique salt. 15 minutes, okay. So you can see here, here's the boiled down version of it. In this case, This hash function MD5 has something called a block size, so that's how big a chunk of data it looks at a time, because a hash function can take infinite amount of data, but it needs to chunk it up into blocks. In this case, for MD5, the block size is 64 times 8. What is that? 1024 bits or something like that. So, that's the salt I chose in this case.
About MD5 and the salt, what's the difference if we have salt and hashed password and it's stolen? We do the same as encryption with salt for our dictionary.
So in this case, the problem is that before, when I did the dictionary attack, if I just go back a bit. So here, the dictionary attack, so the words up here is just an array. So in this case, with the demo that you can view online, on Unix systems as a word list. So I just took the word list, took every single word, hashed it, and then I have a big table of what words map to what hashes. But the thing that the salt does is that then for every single password I wanted to try out, I would need to take that specific salt, do it for the whole dictionary again, and then check. So for every single user, I would have to make a unique rainbow table. So that just means that if you have 1,000 users, then you need to have 1,000 rainbow tables, and however many words are in your dictionary. So the dictionary can be like huge, 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 depending on how random people choose their passwords. And that's probably a pretty important point. The biggest weakness, even though we use all these strong hash functions that I'm going to show later, the biggest threat to people's passwords is still using weak passwords or very predictable passwords. So password 1 or Honda 2 or battery horse stable for the people who are into the field. So yeah, this salting, it's a good idea, but these companies, they still did it in a bad way. Dropbox is the only one that were trying to get away from it. They used SHA-1 with salting, and they're trying to migrate people to go over to Bcrypt. So every time you logged in, if you had a SHA-1 hash in the database, they would ask you to, or they would just rehash your password with the Bcrypt algorithm and put it in the database to keep your password safer. But it was not good enough. So the problem is that these hash functions, I've kept saying it a couple of times now, cryptographic hash functions, they are very, very efficient. They're designed to be very fast. And that is the problem. It's too easy to use them and build these big rainbow tables. So what can we do? Just burn all our money, spend more resources. So here we can use something, it's pretty simple. Just do the hash function over and over again. It's called iterated hashing. There's an algorithm for this. It's in Node Core. It's called PBKDF2. So it's password-based key derivation function 2. If you use this, you are actually NIST compliant. NIST stands for the National Institute of Standards and Technology. It's the it's a big body in the US who decides what crypto functions can industry use. This is how you do it in Node. You use a salt, like before. So you build on the same idea. Then you use how many times do you want to run the hash through the hash function. Then you have to choose how long does the hash have to be, and then you have to choose your algorithm. So suddenly you have all these parameters you need to keep in mind, and you also have to save all these parameters into the database. In this case, I have chosen a iteration count of 10,000, and let's see how fast this runs on my computer. So remember, I have a really slow MacBook here. So first we need to register the user. That's going to take a while. And then we need to first verify the right password and then the wrong password. You can see this is taking a long time because I used so many rounds. So here I'm taking the SHA-512 function. I give them my password, the output of that. I feed it into SHA-512 again, take the output, do it again and again. So you can see now I just verified the true password. And now it's then going and it's trying to verify the wrong password. So you can see it takes a while. So suddenly you're starting to actually get somewhere, and this is why it's accepted by the NIST that this is a valid way to save people's passwords. And that's what Dropbox used. Bcrypt is essentially also a iterated hashing function. It uses a block cipher called Blowfish. And that's one of the algorithms you can use if you have it available. So like all these examples, they are based on Node.js. Maybe you program Python or .NET in your daily work. And Bcrypt is, because it's old, it has bindings available in pretty much all the languages. But the problem is, I'm going to show you. So I have this little bench set up here. We are going to run the, what's the number 5? The iterated password. And so we are burning a lot of resources here. We are burning a lot of CPU. Let's run this. Over here I have top. Top you can use to inspect how much CPU and memory a process uses. You can see the node process is just spinning my CPU. It's just taking up all the available CPU computation I have. But it's not using a lot of memory. It's using like 9 kilobytes of memory. Today, graphics cards have upwards of 12 gigabytes of memory and thousands and thousands of cores. So just think about that. That means we could take this PBKDF2, we could put it on a GPU, and we could do millions of hashes a second simultaneously, and then try out a lot of different dictionaries on a lot of different passwords. So even though it takes a long time, you can just go to Amazon and you can just buy a whole heap of servers, and you can just try out all the passwords with all the dictionaries that you can find. And people actually do this. So if I had a really long password, it might take upwards of 40 years to break that. 40 years sounds like a lot of time. We don't have time to wait for 40 years, right? But the thing is that I just read a quote the other day from an American professor in math, and he was studying some special curves, and he had to try out all these curves, and it took a lot of CPU power, and they didn't have time at his local supercomputer at the university to try it out. So he went to Google, and in an afternoon, he, for a very modest amount, bought 60 years of CPU power. So it might sound like a long time to like 40 years to break a password, but if it's a high-value target, you just go to Amazon, you spend a couple of $1,000s, and you break the password, and then you might be able to log into their banking account or the Facebook or, I don't know, the Pentagon or whatever. So when you think about breaking passwords, you don't think about the time. You have to think about the dollar amount. How much money does it cost me to break this password? And the thing I mentioned before about SHA-1 is that there was some attacks made on it a couple of years ago, and people were really scared that collisions, like so two values that map to the same value, they might be feasible to find, and their estimate a couple of years ago was that it would cost $170,000 to do on in cloud computing. So $170,000, then you have like the target that you're attacking has to be worth a lot of money to you, but due to Moore's law and all that, it just goes, the price just comes down all the time, and it's just a couple of months ago that they actually found a collision, and that collision can be used to craft PDF files that have the same hash, but have different content, and you could put a virus in there, whatever. I mean, PDF has a pretty bad track record, right? So, okay. We saw that the problem is that we are burning a lot of CPU cycles, but the problem is that we can just parallelize it. So let's burn more money. Let's just make it even more expensive to run. And this is where the modern standard comes into play. We're going to use what in the literature, a lot of the functions I've shown so far can also be called key derivation functions. But here we are going to, I'm going to talk about a key derivation function that's designed to be purposely slow. You want it to be really, really slow because it maybe, I mean, it seems counterintuitive, right? You're spending a lot of your own resources every single time a user is logging in. You are delaying them on purpose, and you're burning your own CPU money. But this is an arms race. If you are burning this money up front, an attacker would also have to burn all this money, and if you make it prohibitively expensive, he will not be able to break all the hashes in your database. So before we spend a lot of computation, the other vector we have is to spend a lot of memory. So here I'm going to show again a script that I made. So this, or maybe I'll just show the code first. Yesterday, I made a module. It's called Secure Password. Go and use it. If you don't have time to think about all this crypto stuff, just use this. I'll take care of all the security. I already have taken care of all the security. you can just drop it in. It will make sane defaults for you, so you don't have to think about hash functions, you don't have to think about the parameters, the salts, you don't have to think about anything. Let's just see. This is how you use it. I mean, it doesn't get much easier than this. You just give it a password, it will hash the password for you, it will take care of all the parameters. When you want to check the password, you just call verify, and it will verify the password for you. So it's very easy. This secure password library uses a hash function called argon2 in 2013, because there had, through the years up until 2013, there had been so many breaches and people were still trying to improve the state of the art with the old algorithms that the academic community sat down and said, okay, we are going to make a competition. You can win all the glory in the world if you make the best password hashing function that will go into the next NIST standard. And so this was like a small academic war. People designed functions, and then you had these rounds where people were trying to break the functions, and then you had another round where you could improve the function, and so on and so forth. So now I'm going to show you. So this was just using secure passwords. This is with the default, so it seems to go really fast, but if you have to do this across a database of like a million passwords, and you have to try out all these dictionaries, this is going to be prohibitively slow, even though it looks really fast. I'll just run it again and you can see. Okay, so it goes really fast. If we crank up the settings, we're kind of getting into the same situation as with the iterated hash function. And if we look at this in top, you can see it's spinning my CPU again, but now it's using like half a gig of memory. And if you have a graphics card that has 12 gigabytes of memory, okay, then you can run 24 of these hashing functions at the same time. 24 compared to millions, that's not very much. So the problem here, and I don't know if you noticed, I'll just show it again, is that notice blocking. So if we look at the code, here's the code for the secure password. You can see I tried to schedule a set timeout that will log out hash in the console. The problem being it doesn't come out. I mean, it came out here last, but I mean, it should have come out at the same time. If you're doing this inside your, I don't know, Express router, you're hashing people's password in this way, you're just back to the way we did it in PHP, right? You're just going to block the thread. People have to sit there and wait for a second. Every single of your users have to sit and wait there for a second for the one user to log in. And if you have 1,000 users trying to log in at the same time, you're going to have a really bad time. So the solution is to make it asynchronous. And that's what I spent all of yesterday doing. So when you just use the default settings I have here, this is the important slide to take home. It will run it asynchronously. It will run it in a worker schedule worker thread on the side. So the Node.js event loop can keep on going, and you can keep on serving your customers. So if we take the non-blocking part, you can see it keeps bringing out hash. So we can sit here and do work, and we can verify then true and false. And these are the results that come back from the hash function. So you can see, even though this is exactly the same parameters, it takes exactly the same time, but you can see it's still staying responsive. To dig a little bit into how it works, we are not using the crypto module. So a lot of people, we are using a cryptographic library called libsodium, and me and my friend Matthias, we've made a native binding, so it is a native module, but we spend a lot of time making sure that it runs on both Windows, Mac, and Linux. And when you download it, unlike a lot of the other native modules, it doesn't have to build, so you are not going to run into errors with compilers and all that stuff. Matthias has set up infrastructure, so it does what's called a pre-build. It compiles all the native modules on the different operating systems, and it ships with that. So when you download it, it just runs straight away. We're also going to make a JavaScript version. So the problem here is this is C. You can't ship C to the browser. So we're working on a project called Sodium Universal. So you can also run a lot of these crypto functions in the browser. It's probably not a good idea to hash passwords in the browser because it's so resource intensive, and it is an arms race. If you're suddenly taking the penalty of running something in JavaScript, that's just going to make it easier for your attacker because he's going to run it in C, right? So The module is called Secure Password. It's on GitHub now. It works. It's also going to help you if at some point you get faster servers, so you want to upgrade the parameters, you want to make it harder to crack the passwords. It has that built in. And I'm also working on functionality for it to help you generate secure passwords for your users. So that was it. Do we have time for questions?
Okay, what do you think about using emojis of Unicode in your password? Will it be better and would it be harder to predict such password?
Yeah, okay. That's actually one of the things I left out from the slides here. I wanted to talk about how to measure the security of a password. So obviously, if you just put in password 1, which is like the most common password in all the leaks that have been out, it's going to be really easy to break, because a adversary, a hacker, he's just going to take all the previous leaks, just score them after how probable is it for people to use this password, run it through the hash function, and if he's lucky, he doesn't have to spend that much time trying to find the all the insecure passwords. The best thing you can do is to use a totally random password. I mean, you can't even pick words, like pick totally random letters. The problem is people, like humans, they can't do that. People inside their brains, inside people's brains, inside my brain, there's something we in mathematics called a Markov chain. So when you press one letter, you're going to be very likely to press some letters more than others, and then you are losing what's called entropy. So entropy is like the measure of randomness. Estimating entropy, figuring out how random something is really, really hard. I mean, some of the people, some of the companies that have imposed passphrases instead of passwords, so you have to have like a really long password that's composed of words. That seems on the surface like a really good idea, because then you have to go into the dictionary, you have to combine all the words, and it's going to be really hard to run computation-wise. But what people do instead is they pick their favorite quote, or they pick a line from their favorite song. And if I was an adversary, the first thing I'd do was go onto the internet, download all the song lyrics in the language I was trying to crack, and just try them line for line. That's much faster than trying to combine the all the different words in the dictionary. So yes, putting Unicode in there is pretty good. I mean, the best thing, if you're tech savvy, I mean all the people here are tech savvy, right? So the best thing you can do is use a password manager and use cryptographically strong random passwords. But the longer the better. Yeah.
Hi, thanks for the talk. Very interesting topic. You mentioned password manager right now, and I just wanted to ask, what do you think about these password managers? Like the biggest one, for example, at some point of life, I decided that I will give all my information to Dashlane, for example. I trust this program. And I understand that if it will be broken, I'm totally screwed, but I hope the guys there are safe enough. So is it secure, in your opinion? Is it safe to trust the password managers, for example?
I mean, I'm a special kind of person. Like, look at my face, right? I have a big crypto beard, so I don't trust any third party. So, like with Dashlane or LastPass, you have a third party that holds onto your passwords for convenience. Like, you can log in anywhere, right? And you can have browser extensions. I don't use any of them. I use KeePassX. It's has a local encrypted database. It doesn't back it up anywhere. You have to take care of all that yourself. There's no browser plugins or anything. But it has a very good track record. It's been around for a long time, and I don't have to trust anyone but myself. So, but actually, me and Matthias were talking about it yesterday, and I think we're going to build a password manager that's peer-to-peer. So, like, if you want to learn about the peer-to-peer stuff, go to his next talk, and here you have the secure password stuff, and then you could also build your own password manager. So yeah, but I don't trust any of the big companies. I mean, you have to make the trade-off, right? It's the trade-off between security and convenience. So do you trust them enough? And I mean, they have a big user share, right? So if their cryptography is broken, then it's gonna impact a lot of people. So it's kind of like when you take an airplane, do you expect them to crash or not? I mean, it's a bet, right? But it's a bet with a very small probability. But if the airplane crashes, it's everyone on the plane that dies. It's kind of the same thing. Yeah.
Hey. I just wanted to ask, did you test it with the big amount of authentications? Like many people wants to log in,
Yeah.
and obviously if it would be like thousands of people
Yeah.
who wanted to log in,
Yeah.
it should take a while for them.
Yeah, it will.
or-
It will, and that's that's exactly the point. I mean, we were talking about this too, me and Matthias. I mean, you're not gonna get magic CPU power out of nothing for just running it in separate worker processes, but this is a trade-off, right? You want to burn a lot of money. I mean, you want to burn a lot of CPU. You want to burn a lot of memory, so that and that's most likely when you're gonna be compromised, an attacker has to burn a lot of money. Like the whole point is to make it not worth it to try to crack your passwords. So that does mean that in the long run, you're going to spend a lot of money just for people to log in. But if you think about it, I mean, how often do you log in? I don't know if you have Facebook, but I mean, I don't remember the last time I logged into Facebook. Yeah, right. So you can do a lot of other things around that. Like you can use Remember Me tokens to make sure that people don't have to log in that often. But it's a trade-off. Do you want to keep your users safe? Then you have to spend all these resources. But yeah, that does mean that when you have this login service, you have to take into account that you need to plan for a lot of people to log into the same time. You have to try and estimate, okay, how much CPU power do we need to have available? Do we need to have spare?
So that was actually my question. Do you have some numbers?
I don't have any numbers, but you can see it on my computer. Like, so this is a really weak MacBook. What does it have? 2 cores, I think. Has 8 gigabytes of memory, but it's an old processor and it runs at 1.3 gigahertz. Oh, where does that go? Okay, so that's gone. Oh yeah, here it goes. 1.3 gigahertz, right? I don't know if M7 has 2 or 4 cores, but it didn't take long to run the default settings here that are. These are the default settings. They are of a magnitude where it is still very, very expensive for an attacker to crack a whole database of hashes and mount a dictionary attack. So, and you can see that was pretty fast, right? I mean, on my shitty MacBook here, I could log in a lot of people at the same time. So, but I mean, that scales. If you have a lot of users, you probably have more money to spend on this, and then you can just buy big-ass servers. It's just raw processing power.
Sure, thank you.
Yeah, that's okay.
Thank you for your speech. It was great.
Thank you.
Could you please tell me what's, for your opinion, the best way how to store salt? And what do you think about using of several strings given from different places as salt? Just concatenate them to say.
I don't like either. So that's why I made this module. Here, it does the sorting. It saves all the parameters for how to hash the password, so when people come back and have to verify. So that way, you don't have to think about the salt. I take care of the salt. You don't have to think about how many random bytes do I need to put in my salt. I take care of that. And taking salts from different places, it has to be totally unique for every single user. So there's no point in having pre-generated salts. You just, I can show you what it looks like on the. Well, it looks kind of like what I did with the MD5, even though it was it's MD5, so it's a really bad function. But random bytes, these are going to be cryptographically secure. They are based on entropy that's unpredictable. So even if you were to observe the system over a long time, that's the problem. If you can observe the system and you can see what kind of random numbers is it generating, sometimes you can start to predict what's the next number going to be. You can't do that with random bytes.
Okay, thank you.
That's okay.
What would you recommend for someone who never worked with security to get into it? Where to start from?
Yeah. Okay, actually, until 8 months ago, I didn't know anything about security. Like until 8 months ago, I was still doing the thing where I took MD5 and I made my own loop where I would loop through MD5 a bunch of times, which is like a really, really bad idea. So don't do that. Use my module instead. Or use any module that's secure, but this is the only one I know of that's secure, right? So, but the best way to get into security, First of all, security is like it's like the puzzles you read in a magazine, right? A lot of the puzzles that you're trying to solve with security, they might have like really fancy solutions that takes years of studying math. I mean, I don't understand how a hash function works, actually. I mean, on the inside, I know what properties a hash function has, but were I to open the source code of Argon 2, I wouldn't have any idea what was going on. So that takes a PhD in math to understand. But that doesn't matter. That's not the point. The point is you can reason about the properties. You know a hash function is really expensive to run. You know it's deterministic. You know it's one way. You know it has all the other cryptographic properties I talked about. So the way I got into security was libsodium. So libsodium is the library we're using underneath. It's written in C, and that might scare off a lot of people. But the docs are actually really nice for learning about security. The whole point with libsodium compared to like the crypto module in Node, you get a bunch of different cryptographic functions, and you need to go to university kind of to learn what all these different functions do. And it's very, very easy to introduce very, very subtle attacks in the way you combine these functions. And that's what libsodium tries to solve. So in libsodium, you don't think about the algorithms. You think about the primitives. You think about, okay, I want they have a primitive called secret box. So secret box, you can give it a bunch of data. You can give it a key, and then it encrypts that data with the key, and you can save it to disk, and it will take care of all the encryption and all that for you. So you don't have to think about, okay, what algorithm am I going to use? How do I need to make my key? I mean, what parameters am I going to use, and the block size and all this different stuff. And that's also where we get the password function for the secure password module. And they also have public key cryptography. They have all this interesting stuff in there. And when you read the docs, you start to think, okay, so then I could build this project with these primitives and combine them, or I could build this project. So I want to build a password manager. So I take the secret box and I take the secure password and I put them together, and suddenly it's software engineering instead of mathematics. And that's like something that really motivates me and motivates a lot of other people. And that's yeah, so like go read the docs for Sodium Native. That's really interesting if you want to get into like security. Yeah.